Hello, and welcome to this lesson where we're going to kind of put everything together and really hit the punchline of our discussion of the Laplace transform. In this lesson, we're going to talk about the transfer function, which basically translates into the ratio of the output signal to the input signal, specifically related to frequency. So we want to know if we put a signal of a certain frequency in, what happens to the signal coming out. And it's not hard to see where this is going to become really important when designing filters and frequency-selective amplifier circuits. But for us, filter circuits in the next chapter. We're going to talk about the definition of the transfer function, which we already just said. And then we're going to work out an example where we take a circuit and then figure out its transfer function, but then also figure out the sinusoidal response that that circuit has to a particular input frequency. So let's go ahead and get into it. So as we just talked about, our transfer function is what we're going to define as the S-domain ratio of the input, of the output, otherwise known as the response, to the input, otherwise known as the source. Now, we write this function as a capital H to represent our transfer function, and we'll say that's H is a function of S, and it's whatever our output is, which is a function of X, S, over the input, which is a function of S. And often we just sort of say Y of S over X of S, but a lot of times too you'll see like voltage output, especially when we're talking about our filter circuits, it's going to be voltage out as a function of S over voltage in as a function of S. So that's really all there is to it. There's one last equation though before we go ahead and work out our full example, and that is if we want to know the steady state response of the output. Steady state response. So say, for example, we're interested in the V out, and we'll put steady state as a function of t. It's going to be defined by this equation. A, the original input voltage amplitude, times the magnitude of H of, I'm going to write this as J omega. Don't forget that, let me write it in yellow. Right, that S is just equal to J times the frequency in radians per second. So A times Hj omega times the cosine of omega t plus theta plus whatever our new theta as a function of our frequency is. And that'll be given here in volts. So this is the equation we'll use at the very end to calculate the actual response to a specific frequency. So we're given this signal, or this circuit, that has a voltage source, which we'll label as VG for generator. It's connected in series with this 1,000 ohm resistor, and then it has these two branches, the 250 ohm resistor in series with a 50 millihenry inductor, and then a 1 microfarad capacitor. And the voltage out is going to be the voltage drop on the output pins. And we're also going to make a note that the value of Vs, let me find it, let's say this Vg as a function of t is going to be given to us as 120 times the cosine of 5,000 t plus 30 degrees and volts. And all we're going to be asked to do is find V out of t. Find that steady state output response. So as we just talked about, that's going to be a function of our transfer function. So the first thing we need to do is find the transfer function. Find the transfer function. H of S. Now to do that, we're going to need to work through all of the steps for circuit analysis that we've already been talking about. All those examples that we did in the previous lessons, we're going to need to go ahead and do that because the first thing we need to do is find V out. So let's just go through those steps. Remember step 1. Hopefully you guys are bored of hearing all these steps now. But step 1 is the initial conditions. In this case, there are none, so we don't need to worry about it. None. Step 2 is the sources. Now, we're going to pretend that we don't know this yet. We don't need to know what our voltage is, or what our voltage signal is in order to get the transfer function. And in fact, we'd prefer to have it without knowing what the input signal is so that we can give it any input signal that we want. So we're going to assume that VG is undefined. So our sources, we would say here, are that there are no defined sources for our analysis. Then step number 3 is our symbolic voltages and currents. For this particular analysis, there are 2. We'll have that little VG becomes capital VG, and little V out becomes big V out. So there we go. Next up, step 4, the circuit elements. So let's go find those impedances for all of our circuit elements. If I scroll back to the top here, I'm going to count, let me use yellow, this 1,000 ohm resistor as R1 and this 250 ohm resistor as R2. So we know that our resistors don't change at all. So ZR1 is equal to just 1,000 ohms, and ZR2 is equal to 250 ohms. Now our Z for the inductor, Z sub L, don't forget, is equal to S times L, which is going to be equal to S times 50 times 10 to the negative third, since it was 50 millihenries, which I'm going to go ahead and simplify to be S over 20 ohms. And then we need our impedance for the capacitor, so that's going to be 1 over SC. So that's 1 over S times 1 times 10 to the negative 6. And that's going to be equal to just 10 to the 6 over S ohms. So now we're ready to go ahead and draw our new circuit. So let's see, we've got our big VG source in series with 1,000 ohms connected to 250 ohms. In series with, excuse me, not 5, S over 20 ohms. And that's in parallel with our capacitor that has 10 to the 6th over S ohms. And we're still hunting for this voltage V out across the terminals of the capacitor. So the way we're going to solve this one, there's a couple of different ways you could solve it, but the way I'm going to solve it is with our node voltage. So I'm going to write one node voltage equation that ties, let's see, that current, and that current, because that'll give us a function of V out and VG, which is pretty darn helpful. So let's say this first current is just VG Remember, the voltage here at this node is actually what we're looking for, V naught. So that is going to get us, so the first equation is Vg minus V naught over 1,000 plus, then we have what, V naught over the sum of 250 plus S over 20 plus this last one, V naught over 10 to the 6 over S. That's equal to 0. Now I'll leave this next part up to you, but you're just going to algebraically solve this for, so I'll say solve for V naught, and that's going to get you this. V naught is equal to 1,000 times S plus 5,000 times Vg over S squared plus 6,000S plus 25 times 10 to the 6. Now that means to get our transfer function, our h of s is equal to v naught over vg, which means we can just bring our vg down under v naught, and that's going to get us our final answer for the transfer function, which is 1,000 times s plus 5,000 over s squared plus 6,000s plus 25 times 10 to the 6. So there we go. There is our transfer function, h of s. Now, if we want to find the steady state response, all we need to do is, we'll scroll back up to the top here and see what was our function. We had, in what we were given, our omega was equal to 5,000 radians per second. So we're going to go ahead and just plug that into our h. So we're going to say h of j times 5,000 is equal to 1,000 times j 5,000 plus 5,000 over j 5,000 squared plus 6,000 times j 5,000 plus 25 times 10 to the 6. And if we distribute everything through and sort of simplify it a little bit, we're going to get that we have 5 times 10 to the 6 plus 5 times 10 to the 6 j over minus 25 times 10 to the 6 plus j times 30 times 10 to the 6 plus 25 times 10 to the 6. Now, since 10 to the 6 appears in every single term of this, I'm going to go ahead and lose it, and we'll get that our response here is just 5 plus j5 over minus 25 times 10 to the 6 plus 25 times 10 to the 6 is 0, so it's just going to be over j30, which we can simplify to be just 1 plus j over j to the 6th, which if we bring the j to the numerator, we're going to give us 1 over 6 minus 1/6j, which we need to convert into a phasor so that we can get our two components. So we'll say here that it's equal to the square root of 2 over 6 at an angle of minus 45 degrees. Hopefully you guys are pretty comfortable converting rectangular form into polar form phasors. We did it a bunch in like the first chapter of this course. So if you're still sketchy on that, go ahead and review that. Now we're ready to get our final answer here, which is that our steady state V out of t is equal to 120 times the magnitude, which was square root of 2 over 6, times the cosine of 5,000t plus 30 degrees minus our 45 degrees from our response, and that's given in volts, which means that the final answer for this example is our steady state response. If we give it that input signal V out of t is equal to 120 over 6 is just, what, 2? No, 20. So 20 times the square root of 2, whatever that is, times the cosine of 5,000 t minus 15 degrees in volts. So that's what we need to be able to do in order to analyze our filter circuits that are coming up in the next chapter. So just to recap, the transfer function is pretty simple. It's just the output signal over the input signal. We can apply it to our input sinusoid to get our steady state response. And we just worked an example of, you have to sort of start by doing that Laplace transform method analysis that we talked about in the previous examples, where you just go through the process until you get the thing that you're looking for. And then you're going to solve for your transfer function. In this case, it was V out over VG, gave us a transfer function. Then you're going to apply the frequency, in this case J5000, to that transfer function to get your output phasor, or your response phasor, I should say. And then you feed that into this final equation that you got to get your output voltage signal. So there we go. That's our transfer function, or specifically how we use our transfer function to figure out what our frequency response of our circuit is, so that we can calculate what our output signals are going to be given a specific input signal, especially a given input signal of a specific frequency. Hopefully that wasn't too bad. Hopefully we've worked enough examples where you can kind of see what this process looks like. In the homework assignment for this particular chapter, there's some extra sort of problems that you have to solve. Mostly that has to do with different applications of the circuits one stuff that you did, like finding Thevenin and Norton equivalent signal circuits and stuff like that. But the key process here is to follow that sort of 5-6 step Laplace transform function. And the major takeaway is how to use that then to find your transfer function, which for us will almost always be V out over V in, and use that to find the frequency response of our circuits. We're going to apply this in a big way in the next chapter, which is really kind of the sort of high watermark, the climax of the entire course, which is designing our filter circuits. And so being able to find those transfer functions is a really critical part of that. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I look forward to seeing you guys in the next chapter, where we're going to design some filter circuits. So see you then.